Okay, let me show you why interferometry is such a sensitive measurement of distance, of differences in distance. Here I have set up the two-slit experiment, and these two slits, this is the same as the two water wave experiments where we have two water sources that are tapping the water, or two slits where we have a wave source behind the wall and they're coming through the two slits. And the screen across the way has, the red dots are just meant to be an interference pattern. The red dots are the points of constructive interference, where the term that I didn't use before are the waves are in phase. The destructive interference points are in between those points of constructive interference, where the waves are out of phase. I didn't write that down. That's just the in phase and out of phase. And then there's going to be, sometimes, depending on what kind of pattern this is, it'll really be just shading. It'll go from dark to light to light to dark to dark to light. Here I've just drawn it as dots, as strict dots, instead of it just getting slightly lighter and darker as we move along. In any case, what I want to show is the geometry of how we calculate how the lengths in this experiment are dependent on the wavelength of the wave and the distances in the experiment. I don't know if that made sense, but we're going to do a calculation that shows the relationships between all the variables. My center line is my primary axis, right, where we are definitely, the center line is obviously equidistant from each source, so we would have a constructive interference point along the center line. Okay, so let's go ahead and draw, let's just look at the first point of constructive interference away from the center line, going downwards. So now think of the two slits as two sources, which they are. And what I'm showing with the red lines is the wave that goes to that first interference point. I didn't quite make them meet at the interference point. That was just bad drawing. But what I've shown is that the wave source on top, the higher slit, must travel farther to get to that interference point than the wave on the bottom. And so what I've done is I've dropped a perpendicular, right there, from one line to the other, to show the extra distance traveled, right? The extra distance traveled, is that little piece right there. That's the extra distance traveled. And we can show, I didn't draw this picture quite big enough, but we can still show that if the distance between slits is delta S, and the angle of either of these lines, now here's where we make an approximation. The angle of either of these lines relative to the center axis is theta. We're making an approximation now that delta S is small compared to L. If delta S is small compared to L, therefore the angle theta made by either of those lines is approximately the same, very much the same, and this approximation is a good approximation. And that angle theta can be taken to be either one of those sources relative to the principal axis. And I said it, but I didn't write it, that this extra distance is what we call delta D, the extra distance traveled by one over the other. And so now it is a simple case of showing that delta D with this geometry must equal delta S sine theta. If you don't see it, look carefully, right? I'm going to highlight and then erase the highlight again. This little black triangle has the geometry that we just wrote down. Delta D equals delta S sine theta. Actually, I'm not going to erase that highlighting. Then remember, for the first point of constructive interference, right, delta D over lambda must equal 1, right? Delta D must be 1 lambda. Delta D must be, 1 lambda, that we've shifted everything by 1 wavelength. Or, in general, delta D over lambda is equal to n for any of the points of constructive interference. So delta D over lambda is n for constructive interference. What about, interference. What about the points of destructive interference? the points of destructive interference, you can do the exact same geometry, there's nothing different, and show that delta D over lambda must equal n over 2. So n over 2 for destructive interference. Hopefully that makes some sense the way I wrote it, but let me rewrite it on the next page. I forgot to say, when for the destructive interference, delta D over lambda is n over 2, that was for odd n, right? N is an integer, sorry, n is any integer. And this is going to give you all the points of constructive and destructive interference. Okay, just to give a sense of size scales here, let's just talk about green light, 5 times 10 to the minus 7 meters. And let's just take 2 slits on a piece of cardboard, about 1/10 of a millimeter. That's small, but you could definitely do that. Right, 1/10 of a millimeter. Millimeter is pretty easy. 1/10 of a millimeter, pretty difficult, but you could do that with a magnifying glass and a laser and a razor blade. And let's see where the first constructive interference point is off axis, right? That's the not the center axis, but the first one down that I've drawn in this picture. And so let's go ahead and calculate that. So I'm simply going to ask, what is the angle, right? I'm going to ask, what is this angle here? So I'm going to say the first constructive interference point, n equals 1. So I'm going to use these two equations together and say that delta S sine theta, which is delta D, over lambda equals 1. That's the first constructive interference point. So therefore, sine theta. And so from that, we can just plug in, solve for sine theta. And what we get is that sine theta is 0.005. So plug that into your calculator, and you get, oh, theta is 0.005 radians. Radians, right? We can change that into degrees. Okay, that's 0.14 degrees. You say that's not a big angle, but think about how far away the screen is from the 2 slits. You can set that, right? But let's make the screen a meter away from the 2 slits so that if L equals 1 meter, go back and look at your picture to see what L is. If L is 1 meter, therefore the first dot, right? If the central axis dot and the first dot is down some distance, so we need another distance variable here, but P, right? We can figure out if this is L, this is theta, we can say that P over L equals sine theta. So therefore, P is L sine theta, which is 0.005 meters, or 5 millimeters. Definitely measurable. Okay, so we can measure the distance between the dots. We can definitely measure the distance between the dots. 5 millimeters between the dots. Now, this doesn't quite tell us how sensitive an interferometer is, because we need, in an interferometer, in order to measure something that's moving, we need a change in the pattern. So the question is if I shift one of those sources by a very little bit, how much am I going to change the pattern? So let's say, so here's the key. I've written it down already, but I'm going to explain it. So since a path length difference, right, in this case we had a path length difference of just one wavelength. A path length difference of one wavelength created a interference point 5 millimeters down the screen. An additional shift of one more wavelength means an additional shift of 5 meters down the screen. So this is a really sensitive measurement to changes in path length, because now if I take one of those sources and I move it one wavelength farther away, then the entire interference pattern will actually shift down the screen by 5 millimeters instead of 5 times 10 to the minus 7th millimeters. So this is a very sensitive measure in changes in distance. We'll do that again for the Michelson-Morley experiment. I'll show you what that means there.